Hello and welcome to this electrical principles training video. In this video we're going to answer a question that's come in from a viewer, and this question has come from Jack Cookson, who also happens to be a country singer and makes his own music. So I'll leave a link in the description below for you to go and check out his YouTube channel, which is really interesting. He's got some great songs on there and also on other streaming platforms for music as well, like Apple Music and Spotify and so on. So do go and have a listen to his music and tell me what you think of it. But we're going to turn our attention to the pressing matter for this video. So the question that Jack has sent me is the one that's on the board here. So we've got an image here of a circuit with 4 resistors. The circuit is partially connected in series and partially connected in parallel, which is an interesting one. And I've not written the questions down because ultimately all you've got to do is find the values of the resistors and the total resistance. So the question was broken into 5 parts, and it was A, what's the resistance of R1, B, what's the resistance of R2, and so on and so forth, and then finally find the total resistance of the circuit. Now it's an interesting question because actually you could, just with the information that's on the board here, you could jump straight into figuring out what that total resistance is. However, we're going to break it down and do it in stages, and then I'll show you what I think was probably the lecturer's preferred method for the learner to try and find the total resistance, and then how we can find it really quickly and easily as a quick check in case that's not possible in other questions of this type. So I always really like getting questions like this in, so if you've got anything like this, please reach out to me on Instagram or Twitter or here on YouTube. Please send me a message, get in touch and ask me a question. I can't always guarantee that I'll be able to answer your question with a video, but I'll always try because it's always worthwhile and there's interesting questions come up, especially ones a bit like this. So let's get stuck in to solving the answer to this question. Okay, so I've not got a huge amount of room on the board here, so I'm going to pop this probably in fairly random places as I go along. So the first thing that we need to do is try and figure out what R1 will be. So this is a nice simple one. We've got a voltage of 200 volts supplying the circuit as a total. 10 amps is flowing into the circuit. Now we know from other videos in this series that the current flowing into the circuit must be the same as the current flowing out of the circuit, and there's also some other interesting points that we can draw out as we work along the way here. However, we've also got here 100 volts that has appeared across this resistor. So this question is really looking for us to concentrate on the resistances, and to do that we need to use Ohm's law. So we've got a voltage, we've got an unknown resistance, and we've got a current. Now we know what the current is flowing through this resistor because if you follow the track that the current takes, it comes from the supply, it goes up this conductor here and it enters the resistor here, and you can see there's nowhere for that current to branch off, there's nowhere different for it to go, so therefore the 10 amps that's flowing through this part of the circuit must also be flowing through that resistor. There's absolutely nowhere else for that current to go. So if we've got 10 amps here, we must have 10 amps flowing through that resistor. So we now know the voltage across the resistor because we've been given that in the question, and we also know the current flowing through the resistor. So that means that we can use Ohm's law to try and figure out what this resistance will be. Now, when we start with Ohm's law, the way I always like my learners to remember it is as follows: I equals V over R, like that. So that's the way I like my learners to remember it, because that's really kind of the most real world application of it that we can get. It's describing what happens when we apply voltage to a resistor, which is what we do whenever we wire a circuit up. So I think that's the best way of memorizing it. I equals V over R. And we need to transpose that. We want to get R by itself. Now we could use the Ohm's law triangle at this point. There's absolutely nothing wrong with that, but I prefer to kind of look at it in a slightly different point of view, because that triangle won't help you out of every single situation. When you get other formulas that are a little bit more complicated, it does get a little bit more tricky. So I like to just work straight through the transposition process. So if we look at this, we've got I equals V over R. We'll do that once here, and then we'll be able to apply that to lots of the resistors in this circuit. So we know the current, we know the voltage, we're trying to find the resistance in this case. So we need to get R by itself. So again, we look at this side of the equation, and remember, when we're transposing, what we always do is we look at the order that the operations are being done in, and then when we start to transpose, we reverse that order of operations. Now this one's really easy because there's only one operation. We've got voltage divided by resistance. So therefore we've just got to think to ourselves, right, we want to get R by itself. Now we can't move this V over straight away because we're doing something to that voltage. We're dividing it by the resistance. We're not sort of taking the resistance and doing anything to it with the voltage, if that makes sense. So what we're going to do is we're going to say, what's the opposite of dividing by resistance? Well, the opposite of dividing by resistance is simply multiplying by resistance. So we're going to say we're going to multiply both sides by R. I'll show you the long method on this because we're only going to do it once in this video, so we'll do it thoroughly. So we're going to multiply both sides by R. So we've got I times R is equal to V times R divided by R. So what we're going to do is we can look at this right hand side now and think, right, well, I'm timesing by R and then I'm dividing by R. And if you multiply by a number and then divide by that same number, it effectively cancels out. You get back to where you started. So take any number, times it by 2, divide it by 2, you get back to where you started. And that's true of any number. So we've got V times R over R. So those two simply cancel out. They no longer count. And we're left with I times R equals V, which looks like that. I have to forgive my awful writing now. I'm getting to the limit of my comfort zone. So you can see that we've got I times R equals V, which is great, but we want to get R by itself. So what are we doing to this R here? Well, what we're doing, we'll rewrite this up here. So I times R is equal to V. So we've got this R, we want to get it by itself. At the minute we're timesing it by I, because we can flip those around if we want to and it'll still mean the same thing. So we can now think, right, what's the opposite of timesing by I? Well, the opposite of multiplying by I is to divide by I. So if we now divide both sides by I, so we'll divide that by I, and we'll divide that by I, and we're back to the position we were in earlier where we're multiplying by a number and dividing by that same number, which means that that and that cancel out, and we're just left with R is equal to V over I. Nice and simple. Now I know that's taken a long time to get to that point, and you're thinking, well, if I just used the triangle I could have done that in seconds. Absolutely true, no problem. And hopefully if you're not interested in this bit, you've already skipped past it anyway. But it's always a value to get good at practicing transposition. And if you intend to study beyond your electrical course and go on and look at other courses like HNC or HND or beyond that, then getting good at transposition is really important. You're going to need to be able to do that. So it's good to practice when it's simple because it'll make it a lot easier if you understand the principles behind it in later studies. So anyway, we've found our formula. So in this case, we're trying to find the value of R1, which is equal to V divided by I. Now just make sure we get the right voltage and current at this point. What we're going to do is we're going to say, we'll call this V1, so we'll call that V1, that voltage there, and we're dividing it by that current flowing through it, which is 10 amps. So we have got R1 will be equal to 100 volts divided by 10 amperes. Therefore R1 is going to be equal to 10 ohms. So there we go, we found our first resistance in this circuit. R1 is equal to 10 ohms. Happy days, so that's good. We've got our first resistance. Now at this point, I think this is where learners will probably tend to get just a little bit confused here, because you can now see that the circuit has gone from being a series circuit to now having this parallel part to it. Now this is no reason to be kind of worried or nervous, because actually I personally think this question's been made a little bit too easy, really. Once you realise what we're going to do now, it'll kind of click and you'll go, oh, that's really obvious. So if you look here, the current, this 10 amps flows through this resistor, it gets to this point, and at this point it splits. So some of the current goes that way through that resistor, and some of the current goes this way through this resistor. Now the lecturer who set this question has very kindly pointed out that this is 5 amps flowing this way, and therefore we know automatically if there's 10 amps flowing to that point there and 5 amps of it is flowing that way, whatever doesn't flow that way must flow that way, which is Kirchhoff's law for currents. So the current that leaves a connection must be the same as the current that enters it. So here we've got 5 amps flowing that way and 5 amps flowing that way. We must have the remaining current flowing that way. If I was going to set this question, I'd probably be a little bit mean and make that a smaller or a larger current than exactly half. But that's just personal preference. So let's have a look at figuring out what R2 is going to be. So for R2, we can just use this rearranged formula. So this will go a little bit quicker this time. R2 is going to be equal to the voltage divided by the current. Now again, let's make sure that we get the right voltage and the right current. So you can see here, we've got flowing to this point here, and through here we've got that 5 amps. So we know that there is 5 amps flowing through that resistor. But what's the voltage across this resistor? Well, we're told what it is down here. We've got 50 volts across R3, and because R3 is in parallel with R2, therefore these voltages must be the same across here. So voltages in a parallel circuit that's purely resistive and DC has the same voltage across parallel components there. So we've got 50 volts across R3 and 50 volts across R2. So therefore we've got 50 volts, and that's going to give us 50 divided by 5. That's going to give us an R2 of 10 ohms. So there we go. So R2 is equal to 10 ohms. I'm going to put that in green so that we can match the answer to the relevant calculation. Now hopefully what you can tell from this is that if we've got 5 amps going that way and through that resistor, and we've got the same amount of current, you see, this is why I would kind of phrase this question slightly differently if I'd set this as a lecturer. Don't make the mistake of thinking that in a parallel circuit the current is always going to divide evenly. The teacher who set this has made that decision that they're going to divide equally in order to make their numbers work properly. Sometimes this current might be smaller, sometimes it might be bigger. It depends on the size of the resistors here. Okay, so don't make the assumption that the current will always divide exactly in half and half go each way in a parallel circuit like this. That's not the case. It's just for this question that that's happened. Okay, so in this case we've got 5 amps going that way, so we must have 5 amps coming this way, and we've essentially got exactly the same calculation. We could just change that for R3. We've still got 50 volts across it because it's the parallel part of the circuit. Those voltages must be the same, and we've got the same amount of current flowing down this way as we've got going that way. So therefore we don't even need to do the calculation. We can just say that R3 will be equal to 10 ohms again. It's exactly the same calculation as we did just here. Okay, so now let's figure out what R4 is going to be. So R4 will simply be the same calculation again. So we're going to find R4, and we're just going to use again the voltage divided by the current. It's the same calculation 3 different times here. So what values are we going to put in here for voltage and current? Well, the voltage is going to be the 50 volts that is across R4, so that's 50 volts there. And then the question now is what current is flowing through here? So what current is flowing through R4? Well, again, let's trace the currents round. We've got 5 amps flowing up through here, so that comes back down to here and it must flow through there. But we've got the other 5 amps from this 10 amps that's flowing through here this time and up to this point, and at this point they recombine, they join together, and both of those 5 amps must flow through R4. So therefore we've got the addition of the current in this branch and the current in this branch flowing through there, which gives us a total current of 10 amps again. So there we go. So now we've got 50 divided by 10, so we've got 50 volts divided by 10 amps, and that is going to give us 5 ohms. So therefore this resistor here, R4, has a value of 5 ohms. So there we go. We've found the 4 values for the resistors. R1 is 10 ohms, R2 is 10 ohms, R3 is 10 ohms, and R4 is 5 ohms. Again, I'd have done this slightly differently if I was setting this as a question to make those different, because there's a lot of the same numbers here and it's very easy to get all those numbers a bit confused and a bit mixed up with each other. So yeah, I'd kind of done that slightly differently. But again, it's just personal preference. This is one question in a list that I noticed that Jack sent to me, and so it may be that this is like a stepping stone along the way to more complex questions, in which case that would make really good sense. So one thing that we've got to think about now is that final part of the question: what's the total resistance for the circuit? Now, we could look at this in one of 2 ways. I suspect there's a way that the teacher wanted it doing. And to me, that would be that to take these resistances and figure out what the total resistance is going to be. So let's do it that way to start with, and I'll show you the kind of the easy way that we can do just to check that we've got the right answer. So we've got part of the circuit connected in series, part of it connected in parallel. So for this question, we've got to figure out what this parallel part is first, because what we can essentially do is we can almost replace this parallel part of the circuit with one value of resistance, which will then just give us 3 resistances in series with each other. So let's do that first of all. So what will the total resistance of this section be here? Okay, so what will we call this? We'll call this R2, 3. Let's get a different pen so that we're keeping it mixed up. I'm going to turn the other way now. So we've got, we'll call this R2, 3 like that. So this is the total resistance of this parallel part of the circuit. So we're going to say, now again, there's like 2 or 3 different ways that we could do this. It's a really interesting question, and you know, I'm going to ramble on a little bit here just because there's a bit of value to exploring this. We could use the method that suits all resistors connected in parallel, no matter how many you've got, the reciprocal method. So we could do 1 over 10 plus 1 over 10 and figure out what that would be. So let's do that actually, because that'd be quite interesting. So we're going to say that to figure this out, we're going to do 1 over the total resistance of this section, R2 and R3, is equal to 1 over R2 plus 1 over R3, and this is this is quite a good way of doing it. If you're not sure what I'm talking about here with the reciprocals and 1 over and all this stuff, go and check out the videos that I made on this, or really the series of videos that I've made on this subject, because that's going to really help you to understand what's happening here. So we'll put in our numbers, which is 1 over 10 plus 1 over 10. That's going to give us 2 over 10. So remember, this that we found here is 1 over R2, 3. And therefore, in order to figure out what the total resistance for the parallel part of the circuit is, all we've got to do is actually just flip this upside down. So we end up with R2, 3. Now we could say divided by 1, but of course any number divided by 1 is just the number you started with, so we can ignore that bit, is equal to, this bit flipped over, 10 over 2, which gives us 5 ohms. So the total resistance for that part of the circuit is 5 ohms. So in other words, if we just had those 2 resistors by themselves and measured the resistance from one side or the other when they're connected in parallel, we'd get 5 ohms. Okay, which again, you may have noticed, is actually half of one of these values, and that is a really good thing to remember for exam situations. If you've got 2 resistors of the same value in parallel with each other, the total resistance is always half of one of them. But that only works if they're the same value. So don't try and do that if you've got a 10 ohm and a 20 ohm resistor, because it won't work in that situation. So actually all of that was just kind of a load of faff that we didn't really need to do, but it's always good to be reminded of how to do it properly before you learn how to cheat. Let's have a look at another method that we could have used for this one. So I'm going to have pen colours, we're going to go for black now. So we're going to say now that we could find this by doing R2, 3. Make that a little bit big. Get rid of that. There you go. No mistakes, just happy little accidents, as Bob Ross would say. So R2, 3, we could say, is equal to the product over the sum of those 2 values. So I'm just showing you another way to do this. Now, feel free to skip past this if you're not interested and you just want the total resistance for the circuit. But what we've got here now is another way of finding the total resistance of this parallel part of the circuit. We've got R2, 3 is equal to product over sum, and that just means the numbers multiplied by each other divided by the 2 values added together. So in this case, that's going to give us 10 times 10 over 10 plus 10. And that's going to give us 100 over 20, which gives us 5 ohms. So we've got the same answer that we did before, so that method works, which is really good. So there you go, 2 resistors in parallel, same value, 3 ways we could do it. It's either half of one of the values, really nice and easy. We can use the product over sum method, a little bit trickier, or we could use the reciprocal method, which is way too complicated for this situation. I just wanted to show you how to do it. So you can see there we've got the same answer every time, so we're comfortable with that. So now what we've got is effectively a resistor in series connected with another resistor in series here that has the equivalent value of 5 ohms that we just calculated. So it's like these two, we've just found the equivalent resistance of them and put them together there. And then we've also got another resistor connected in series. So to find the total resistance for the circuit, it really couldn't be easier at this point. All we've got to do is say the total resistance will be equal to R1 plus that value that we just figured out for R2 and R3 in the parallel part of the circuit, plus R4, and that is going to give us, again, really nice and simple, we've got 10 ohms that we figured out over here. I'm going to remove that ohms from there because this adds to the confusion a little bit. 10 plus 5 that we calculated here and here, and then plus that 5 ohm resistor that we calculated there. 10 plus 5, which gives us 20 ohms in total. So the total resistance of this circuit is 20 ohms, and we've been through a ridiculously unnecessary complicated method to find that. There's a really, really simple way that we could have done this, and actually I suspect the teacher wanted this more complicated method doing and then checking with the simpler method. What's the simpler method? Well, right from the start of the question, we knew what the voltage being applied to the circuit was, and we also knew how much current was flowing into the circuit. Therefore, we could have just used our rearranged resistance formula, as you've got here, rearranged Ohm's law, and all we had to do, I'm going to finish off in brown because it's the last colour on the board now, we've got R is equal to V over I, and what we're trying to find here is the total resistance, so we're going to use the total voltage divided by the total current flowing into the circuit, which gives us 200 volts divided by 10 amperes. 200 divided by 10 gives us 20 ohms. And there we go. We have got our answer. We've confirmed that the total resistance of the circuit is 20 ohms. So really nice and simple, actually. We've just worked through a couple of different methods. We've done it the complicated way to help us to understand how resistors in series and parallel work. And then we've also just looked at the simple way as a quick check to make sure that we've done our calculations correctly. And indeed, we have. So all in all, quite an interesting question, that one, and quite a lot that we could glean from it. I've probably got into it in a little bit more depth than was necessary just to answer the question, but I'm always very keen for people to understand the subjects we're discussing and not just get to the right answer and get a tick. It's very important that we can get under the skin of the question and understand it properly. So there we go. Thank you very much, Jack, for asking that question. I look forward to future questions from you. If you, the viewer, have got any other questions that you'd like, please leave them in the comment section below or reach out to me on social media and I'll be happy to help you out if I can. All that remains in this video is to say thank you very much for watching.